Welcome to qnawire.
For this question, we're going to consider an atom that has a magnetic dipole, and this atom is made of iron. So the magnetic dipole, which I call mu prime, is 1.8 times 10 to the 23rd amperes per meter squared. So we're going to determine the dipole moment of an iron bar magnet, which has a volume that is 9 centimeters by 1.2 centimeters by 10 centimeters. Or 0.9 by 0.012 by 0.01 meters cubed. So I put everything into meters. So this volume V is 10.8 times 10 to the minus 6 meters cubed. Okay. The other thing we're going to need to determine this question is we're going to need to know the density of iron, rho, which is 7,800 kilograms per meter cubed. We also have the atomic mass of one atom of iron, M, capital M, which is 56 times 10 to the minus 3 kilograms. I also wrote out Avogadro's number, which I called N, and it's 6.023 times 10 to the 23rd. And we're going to use Avogadro's number as well for this. Okay, so for part A, to find the magnetic dipole moment of the iron bar, we're going to first consider the fact that the total dipole moment of the iron bar will be equal to the number of atoms times the dipole moment of a single atom of the iron bar when it is fully magnetized. So I can write out mathematically what I just said. So this is part A. So the dipole moment of the entire bar, I'll call mu, is going to be equal to the number of atoms in the bar, N, times the dipole moment of each individual atom, which is mu prime, which we know. So then the question is, well, what's N here? N being the number of atoms, how do we find that? Well, the number of atoms in the iron bar is going to be given by N is equal to the total Avogadro's number, N, times the mass of the entire thing, little m, divided by the mass of the dipole, divided by the mass of a single atom of iron, the atomic mass. Okay, so, well, what is the mass of the iron bar, M, little m? Well, the mass of the iron bar, little m, is just going to be equal to the density, rho, which we know, times the volume, V, which we also know. So since we know Avogadro's number, since we know rho, since we know V, since we know capital M, which is the mass of one atomic iron, and since we know mu prime, the magnetic dipole moment of one atom, we can solve for mu. We ran out of room on this page, but we'll go ahead and do it over here. We find that mu is equal to N times rho times V divided by capital M times mu prime. So we simply replace all those values with what we had written above, and we find that this is equal to 16 amperes times meters squared. And we can box that in as our solution for part A. Part B says, what is the torque that would be exerted on this bar when placed in a 0.8 Tesla magnetic field at right angles to the bar? So for part B, the magnetic field here, which we're going to call capital B, is equal to 0.8 Tesla, right? And the other thing we need to know is the angle, but it says that it's at right angles with the bar. So the angle theta is going to be at 90 degrees, since 90 degrees is right angle. So then the torque that's placed, tau, is going to be equal to the magnetic moment, mu, which we just found, times the strength of the magnetic field, B, times the sine of the angle that it makes, theta. Well, the sine of 90 degrees is simply 1, so this ends up being mu times B, or 13 newtons times meter. And we can box that in as the solution for part B in the final part of our question.